Good morning. Welcome to the tutorial, pre-recorded self-guided content. So the intention here is that you'll watch this lecture at the beginning of your tutorial session. And then in the second hour of the tutorial, we will be meeting live on Zoom to discuss a few things. So make sure you watch this lecture as well as have a look at some of those reading materials which are up on the Moodle class site under week 1. All right, so we're going to be talking more about water quality and specifically how water quality impacts the environment and vice versa, how environmental factors can influence water quality. So I'm going to start by just showing a brief picture here. So last night we had a little bit of wintry sleet, which was on the deck this morning. The Weather Service was predicting some damaging winds. Thankfully, those did not come to fruition because in our last lockdown, lockdown 4.0, we had a really nasty storm. You might remember it was in the early first or second week of June. You would certainly know if you live in the hills because we had heaps of trees down, and a lot of those downed trees fell on power lines, and the loss of power. Well, I was lucky. I lost it for 2 days. Some of my neighbors were without power for almost a week. But one of the outcomes of the power outages actually had a significant impact on water quality. So there's a reservoir up in the eastern side of the Dandenong Ranges near Callista. And without power, the water treatment facility there can't operate. And as a result, untreated water can become distributed throughout the system. And so in the last lecture, I showed a few screenshots about water quality being announced on the Vic Emergency app. In that instance, it was in relation to blue-green algae and some of the health consequences of that. But in this case, it's about water pollution. And so this is going to be one of the things that we dive into a bit more during the practical, because we'll be looking at some specific water quality guidelines that are measured and assessed in terms of to what standard your drinking water should be. And we'll also be thinking about the quality of water in terms of how it relates to recreational water use and ecosystem health, because the standard of drinking water for human consumption is much higher than it is for plants and animals and other ecosystems. And so that storm actually did impact us a little bit. We had a few limbs down on the property, and it also impacted Jack's drinking water, because as you can see in this picture here, this limb fell right on Jack's drinking water bucket. And so oftentimes that'll be full of rainwater. I also put tank water in there as well. Jack, being a beast, he can tolerate tank water and rainwater just fine. He's happy to drink it, but the standard for my drinking water is a bit higher. But as you can see, Jack was not happy that the limb fell on his bucket. It almost crushed the thing, and thankfully he wasn't there actually drinking when the limb fell. But you know, Jack, he got his revenge. He started to tear the bark off the stick, so I think that made him feel a little bit better. That's enough about Jack. Let's get down to business. Okay, so revisiting the learning outcomes for week 1. In the lecture, which you would have watched prior to this, we defined water quality as well as some key water quality parameters. Okay, what we're going to do now in this content, as well as in the tutorial, is focus on number 2 here and how the environment impacts water quality and vice versa. So I'll briefly go through what we discussed in the Monday lecture and expand on that a little bit. And then we'll focus on some of these environmental impacts from water quality perturbations. Then we'll discuss some water quality guidelines and where we can access that information. And lastly, what I want to do is discuss the connection between water quality to soils and vegetation, or more broadly, the biosphere. Learning outcome 3 will be primarily addressed in this week's practical. And in the practical, we will be looking at water quality data from the Water Watch website. And we will interpret some of that data and practice communicating water quality data through an infographic. All right, so what is water quality? Well, we defined this in the previous lecture. And simply put, water quality describes the physical, chemical, and biological characteristics of water. Okay, and this often includes its suitability for a particular purpose. So the quality of water for drinking, for example, has different guidelines than for recreational use or for the proper health of an ecosystem. Okay, so physical water quality parameters would be, how the water actually looks, what's physically in it, namely suspended solids. Chemical properties would be what's dissolved in the water, and biological, what's living in the water. All right, so we went through these key water quality parameters, mostly defining them in the previous lecture. I'm going to go ahead and expand on some of these and talk about the causes and consequences of issues related to these parameters and how they impact the environment, except for contaminants, because that will be the primary focus of week 4's content. All right, so dissolved oxygen. Okay, remember, 21% of all the air we breathe is oxygen, okay? And that oxygen gas is able to dissolve into water, okay? And we call that aqueous O2. Now, typically there will be a equilibrium between the oxygen in the air and oxygen dissolved in water. And that results in an equilibrium oxygen concentration in the water. Okay, and typically that's sufficient to maintain a healthy ecosystem where aquatic animals, such as fish, for example, are able to thrive. However, there's a number of things that can cause dissolved oxygen levels to become too low. Okay, we talked about this a little bit. Do you remember what those things were? Oh, good, my pen's working this time. All right, so we want to think about the processes that either produce or consume oxygen. Okay, because normally there's a nice equilibrium here between oxygen in the air and oxygen in the water. But if oxygen is being consumed, for example, oxygen levels, dissolved oxygen levels can plummet. Okay, so O2 production occurs through photosynthesis, right? And oxygen consumption occurs through a process known as respiration, or specifically aerobic respiration. There's actually a variety of respiration metabolisms, but aerobic respiration is the most common one, which couples the consumption of oxygen to organic matter. Okay, so anytime we have excess organic matter and usually excess nutrients as well, that leads to an increase in the rate of, or an increase in the amount of respiration occurring, and oxygen levels can plummet. And the consequence of that is that aquatic animals essentially suffocate. And this is a problem throughout, especially freshwater systems. Oftentimes these are stimulated through mismanagement of water systems, so excess runoff of nutrients, which can stimulate algae blooms, for example. And this is just one example of in the Murray-Darling River system. And these fish kills like this, due to low dissolved oxygen, can also be more pronounced during the summer, rather than the winter, because remember, there's a relationship between temperature and dissolved oxygen. Right, turbidity. Turbidity is a measure of the suspended solids in water, okay? They're not dissolved, these are suspended solids. So think of like sediment or soil being suspended in the water. And turbidity is a problem when levels are too high. So what causes this? Well, usually land mismanagement. So in areas where agriculture is occurring would be one example. If there aren't proper retention ponds or retention basins to slow down the movement of water, fast moving water is more likely to pick up suspended solids and carry them into waterways. Okay, and so, clearly this is a big impact on the recreational quality of water. So if we think about the Yarra, for example, if you drive up into the upper Yarra Valley near Warburton and have a look at the Yarra River, you might want to jump in there on a hot summer's day and have a swim. But I don't know if anyone would be particularly keen to go for a swim in the Lower Yarra near Flinders Street, for example, because usually at the lower reaches here, the water is a bit murkier. It has a higher turbidity. So some of the impacts of this include increasing the amount of organics. Okay, so some of those suspended solids can be bits of organic matter, and also sediment particles. Sediment particles can contain organic matter as well, and so that leads to excess food as well as nutrients getting into water systems, which can thus lead to algae blooms. And likewise, turbidity blocks sunlight, and so that inhibits aquatic plants from being able to carry out photosynthesis. And again, the solution to this is better catchment management, okay? Coming up with ways to prevent runoff from storms, for example, from just washing material into waterways. In natural systems, this is usually accomplished through just vegetation, which slows down the movement of water. In urban areas, however, there's a lot of hard surfaces like roofs and pavement like roads. Water can run off quite rapidly and pick up debris with it. Okay, nutrients. So when I say nutrients, this can refer to any element or chemical substance which is typically limited in an environment. However, in most environmental systems, reactive nutrients consist of either nitrogen in the form of ammonia, NH4+, although this would actually be ammonium. Ammonia would be NH3. And secondly, the second reactive form of nitrogen is nitrate. Okay, but in addition to this, phosphate can also be an important nutrient in terms of impacting water quality. And so I guess in this case, there can be problems when levels of nutrients are too low, because there can be virtually no or extremely limited primary productivity, i.e. biological activity. But oftentimes the problem is associated with nutrient levels being too high. Okay, so too much nitrogen, usually nitrate. Nitrate tends to be quite soluble, certainly more so than ammonium. Okay, so nitrate can be easily transported in water and end up in places where it shouldn't be, where it can stimulate phytoplankton blooms. And phytoplankton blooms are detrimental for a number of reasons. Even though they might have a temporary boost in O2 because algae does carry out photosynthesis, these massive blooms that occur in surface waters can block light at lower depths and thus starve bottom-dwelling aquatic plants from sunlight. In addition to this, the algae themselves can produce toxins, okay? So you don't want to drink water which has recently been exposed to an algae bloom. And we talked about this in the previous lecture at Lake Charlegark, for example, in West Victoria. Because even if you boil this water, that doesn't remove the toxins that are produced by the algae. And as is often the case, the solution or prevention of this problem relates to improving catchment management. Although the problem is a bit more complicated than that because it usually stems from agricultural practices as well, particularly the over-application of nitrogen and phosphorus fertilizers. And so if you're applying excess fertilizer, a variety of biological and chemical processes can result in transformation of nitrogen, particularly ammonium to nitrate, which can then leach from agricultural fields into surrounding water bodies. Okay, conductivity. So this is electrical conductivity, which sounds like a funny thing to be measuring in terms of a water quality parameter. But remember, we're not interested in the conductivity in terms of the physical phenomenon there, but rather the fact that conductivity is directly proportional to the amount of dissolved ions or dissolved salt in water. And in many cases, it's, okay, so you might ask the question, well, why don't we just measure the dissolved salt? Why measure conductivity and then convert it to, and use it as a proxy for dissolved salt? The reason is because we can very easily measure the conductivity of water. There's a variety of electrochemical probes, which you can literally just submerge in water, and it gives you a reading, which you can quickly convert to dissolved salt. Whereas actually measuring that dissolved salt in ions would be a more laborious process. So this is an issue, particularly when dissolved salt is too high. Because most plants and animals have a somewhat limited tolerance to salt. Of course, there are exceptions, right? There's mangrove plant species, for example, which can tolerate salty conditions, but most terrestrial plants and animals have fairly low tolerances to this. And oftentimes, to prevent water from becoming too salty, we need to better manage irrigation, particularly in coastal areas. Okay, so one example where this is a problem is when excess fresh water is withdrawn from aquifers and used to irrigate agricultural land. So as you extract fresh water from an aquifer, that can lower the water table. And likewise, if you're close to a coastal area, saltwater intrusion can occur. So that process works by when you withdraw fresh water, salt water can essentially come in from either from depth or from lateral motion to essentially fill that void. But even if you are irrigating with fresh water, over-irrigation can actually result in the accumulation of salts on agricultural land, particularly in areas where there are high rates of evaporation. So most water, even fresh water, still has dissolved salt in it. And when you apply that water to land and the water evaporates, the salt is left behind. And over time, if you repeat that cycle, salt buildup can occur on soils. Okay, last parameter here is pH. So remember, we defined pH last time as the negative log of the concentration of H plus, where H plus is a hydrogen ion. Okay, so this is a little counterintuitive here, but essentially the more H plus you have, the lower the pH value would be. And that's just how the negative and the log works. Okay, so more H plus means lower pH, and lower pH values mean more acidic. Okay, so there's a number of processes that can affect the pH of water. Dissolved gases, for example, can influence the pH. And we talked about this in the lecture, for example. So carbon dioxide in the air can react with water in clouds to form carbonic acid. Okay, and so again, then this carbonic acid can release one of these protons. Okay, and so by generating a proton there, or a hydrogen ion, you increase the amount of that and consequently lower the pH. However, carbonic acid, which is this compound here, is a weak acid. Oftentimes, we can see extremely low pH values. So this process up here, for example, usually results in rainwater of a pH of about 5.5, roughly. And sorry, my head is blocking it there. But when water reacts with certain types of minerals, particularly sulfide minerals, so this FeS2, this is an iron sulfide mineral called pyrite. Some of you might know pyrite as fool's gold. But when pyrite reacts with oxygen and water, it ends up producing sulfuric acid. Okay, and so likewise, this sulfuric acid is actually a strong acid, which means that it will release all of those protons. And so these protons, as they increase, pH decreases, and the system is more acidic. And acid mine drainage, as shown in this image here, can result in pH values in extreme situations as low as 0, but certainly ranges between 1 and 5 are not, between 1 and 3 even are not uncommon, particularly in areas where mining is occurring. Oftentimes ore deposits, for example, are associated with pyrite. And so when we dig up that ore and it reacts with oxygen and water, everything oxidizes to form iron oxides and sulfuric acid. So this is a problem because when pH falls outside of a healthy range, that can be detrimental for plants and animals, but it can also damage infrastructure as well. It can deteriorate concrete and steel and other infrastructure type building materials. And so the best way to manage this problem or prevent it is to, well, eliminate the exposure of this mineral to the air and to water, which requires better management of mine wastes. But it's not just mining. This process outlined in the reaction here can also occur naturally. So in acid sulfate soils in particular, which are quite common around coastal areas in Australia, acid sulfate soils contain minerals like pyrite and other iron sulfides. And when we disturb acid sulfate soils and expose them to air and water, that can generate sulfuric acid, which will make these soils unsuitable for agriculture. All right, so that's a quick review again of some of the water quality parameters, and in particular how they can impact the environment or how the environment can impact them. I want to talk very briefly about water quality guidelines. Okay, so when we talk about water quality guidelines, we're often viewing this through the lens of human or ecosystem health. Okay, so the water quality parameters that are acceptable for drinking water, as an example, are very different from those that determine the quality of natural systems. But when we think about human health, it's not just drinking, but also recreational purposes, such as swimming, fishing, boating, things like that. And when it comes to ecosystem health, it's all about habitability. And the two, of course, are interlinked, right? We want healthy ecosystems in order to, to have a good starting point for water that may be used for human purposes. We want our aquatic systems to look like this, for example, and where we have nice, clear water with low turbidity. And certainly the pH of this system would need to be somewhere around between 6 and 8. Otherwise, that would be detrimental to the aquatic organisms. And we don't want excess nutrients, which might stimulate excess algae blooms, which would choke out sunlight from these subaqueous aquatic plants here. Right, so this is what we would expect a healthy ecosystem to look like, rather than something that's just covered in green scum and with fish floating at the top, right? All right, so we're going to look at some of these water quality guidelines in the practical coming up this week. Okay, so these are regulated to protect drinking water. The composition of drinking water specifically is regulated to protect human health, but also infrastructure. This is regulated at the state level through the Safe Drinking Water Act here in Victoria, but there's also some federal guidelines as well. And so we're going to look through some of these fact sheets in the practical, and we'll be looking specifically at what some of the limits are on various types of water contaminants or components. In addition to that fact sheet, there's a variety of other sources where you can obtain some drinking water and water quality data. So there's this thing called Drinking Water Quality Annual Reports. And so these should be hyperlinked here. If you retrieve the slides, you should be able to click on these, and you can view up-to-date information about water quality in your area. Okay, so water companies are required to regularly test water for things that may be problem contaminants, as well as biological agents, such as E. coli. There's also things called trihalomethanes, which are actually a disinfection byproduct. So the actual disinfection of water for drinking water purposes can generate contaminants, and so they need to monitor for those, as well as turbidity. Nobody likes brown water coming out of their tap. Occasionally there's no health risk even associated with that, but for aesthetic purposes, people want their water to be crystal clear, right? In addition, you can go to specific water providers. So most of you probably get your water from Melbourne Water or Yarra Valley Water. I get mine from Yarra Valley Water. And you can look at water quality reports from those specific municipalities where they analyze water for a variety of components. Okay, so that's for human health, but what about ecosystem health? So it's important that we manage Australia's water resources. And so there are specific guidelines that regulate water for recreational use and ecosystem health. Now, the important thing to note here is that these values do differ than the guidelines for drinking water. And these are set by ANZEC, which is the Australia New Zealand Environmental Conservation Council, I think. Someone can fact check me on that if you'd like. And so we'll be looking at actual water quality data in the PRAC and then comparing it to these guidelines to see if well, particular areas are of good or poor health. All right, and so one of the themes, though, that we should also be thinking about here is that we can't necessarily treat water in isolation because the quality of water is impacted by the environment around it. And similarly, the environment thus has a feedback back onto water quality, okay? So water is interacting with the land, the air, as well as organisms that are living in and around water, right? And there's a lovely feedback between all of these systems. They're interacting with one another, they're exchanging mass. We talked about dissolved oxygen as an example, right? Where oxygen in the air diffuses into water and vice versa. That oxygen is important for organisms. And likewise, the land is also interacting with water. Humans can impact a lot of these exchanges between these environmental compartments as well. And so it's just important to recognize that anytime water quality is impacted, that will have a flow-on effect onto the health of organisms and the quality of soil and vegetation, for example, as well, can have a feedback on soil and water. And so that's sort of one of the themes that should become clear throughout this unit. So in weeks 1 through 4, we'll be focusing on water, but it's important to always think about how water also impacts soil and how soil impacts water. And of course, vegetation is tied in there as well, right? You know, vegetation is pulling up nutrients from poor water. Those nutrients often come from minerals in the soil. The vegetation itself can then influence water quality as well. So what we're going to do for the tutorial is there are 3 articles uploaded onto the Moodle site under week 1. Those are fairly short articles. Go ahead and give them a read in advance if you can. Otherwise, there'll also be time to review them in class. So we'll be meeting starting at the 2nd hour of your scheduled TOOT. Okay, so that would be what, 11 a.m. for the Monday, 12 noon for the first Wednesday session, and 2 p.m. for the Wednesday afternoon session. I think, remember, your primary source of information is the Moodle site, so have a look there, okay? But we'll be looking at how various activities and processes impact water quality, specifically logging, bushfires, and agriculture. And within groups, you will discuss how these processes or activities impact particular water quality parameters. And we'll think about perhaps which one of these is most important for protecting water quality for us here in the Melbourne area, or we could even think about it from a global perspective as well. All right, so I'll see you soon. Cheers.